This is my first recording, so we'll find out how interesting things actually go. Chapter 10, there are three main ideas that we'll be looking at. The first one is conics, which is just in section 1, and we'll be applying conics and with applications to calculus. And then the next two sections will deal with parametric equations, and then the last three will deal with polar equations in calculus. So today is a long section, and we'll break it up into 2 days. And today will just be circles and parabolas, and then tomorrow we'll talk about the ellipse and hyperbolas. So conic sections. For conic sections, by definition, it's the intersection of a plane and a double-nabbed cone. So here's your double-nabbed cone, and obviously different planes that can intersect. The first one is a circle, and you get a circle here when the plane is parallel to the base of one of the cones. And circles are pretty easy to deal with, so that's a nice starting point for us. And then we'll also deal with our parabolas today. And here's our parabola. The line, the plane that is intersecting, is going to be parallel to your double-napped cone. And then the ellipse, here's our ellipse, so that just isn't parallel to the base when it intersects. And then your hyperbola, there are two different situations. The one that we deal with is typically this one on the right, where the two branches are going to be equal, but there's also this situation as well where they don't have to be the same. So we have, they're called general, or the general equation, I'm sorry for this, is ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. And we don't have to have all of these parts contained. Like here we won't have anything with b, your coefficient will be a 0 in that situation. So to start with a circle, definition of a circle is all the points x, y that are equidistant from a fixed point hk. And why this is a definition that they put in all your points x, y is just to tell you that it's two-dimensional. So it's still on your plane. Equidistance, it's one of my favorite words because it combines two words in one. So we know obviously that they're equal distance, and then there is your center hk. Here's our standard equation. X minus h, that quantity squared, plus y minus k, quantity squared equals r squared. If this happens to be centered, the center of your circle is at the origin, then we know that our equation is just x squared plus y squared equals r squared. Typically, though, we're going to make it a little more difficult and not have things always centered at the origin. So a quick example, just to refresh, is we want to find the center and radius of a circle and graph it. Really, we don't, this is nothing to do with calculus, so this is kind of nice. It's just a good old review. Keep in mind, though, when you do complete this square, your leading coefficient has to be 1. So in this situation, when we have 5x squared and 5y squared, that indicates that it's a circle because your coefficients are the same. We will have to factor out the 5. How I do this is I group my x's. So I say here is my 5x squared, and then I'm going to add 20x to it. And then I leave a space. I know I'm going to have to factor out the 5 still, but I usually leave a space because I know I have to complete the square. Then I'm going to add to it. I have 5y squared, and that was positive. This has to be a negative 30y. Leave a space, and then this last minus 5. Really, I don't want to put it with either of those two trinomials, so we add 5 to both sides, and it moves over to the right. From here, factor out your 5s. That gives you x squared plus 4x, and we have to factor the 5 out of the second soon-to-be trinomial as well. And then that's equal to 5. So now to complete this square, does anybody, hopefully you remember how to complete the square. Remember, completing the square, it's half of your b value. And so obviously if in this first situation half of 4 is 2, and then you square that, that will give us 4. What you need to be very cautious about is that you didn't just add 4 to the left, you actually added 20. So make sure you distribute that 5. Well, if I add 20 to the left side, it's only fair to add 20 to the right side as well. And here, when I look at my b value, it really doesn't matter if it's positive or negative, because in the long run, when you take half of it and square it, well, you're squaring it will always become positive. So half of 6 is 3, 3 squared is 9. Again, you didn't just add 9, you actually added 45. So that's equal to 45. And now I can rewrite this, and I have 5 completing the square. My first term of my binomial is x. I am adding, and that follows this operation here. So I'm adding, and then it's half of your b value, so that would be 2, and now that's that quantity squared. Plus 5, that would be my y. Now this time it's minus. Half of 6 is 3. It's that quantity squared. And then 45 plus 20 is 65, plus 5 will give us 70. I have to make this equation look exactly like the standard equation. Therefore, I have to divide both sides by 5. Remember, we only divide once, the left side by 5 one time, because when you divide by 5, you need to divide both terms. So your first term and your second term, you have to divide it by 5. So in the long run, our standard equation becomes x plus 2, that quantity squared, plus y minus 3, that quantity squared, and 70 divided by 5 is 14. Now once I have my equation written like this, we can easily solve many questions. So find the center. Well, the center of this is quite easy. Remember, we have to make our binomial 0. So that would give us, as an x value, -2, and our y value would end up being a 3. Our radius is the square root of 14, because it equals r squared. So that's your radius squared, therefore your radius is obviously the square root of 14. And it does say graph. In these situations, obviously your center should be correct, so at -2, 3. And then here your radius, I don't know exactly the square root of 14, but a little bit more than 3.5. So then it's just an estimate from there. And I'm pretty sure you can graph that on your own. So there's your circle. Really not a lot of calculus again with that. If we move on to parabolas, there are a lot of calculus applications that do go with parabolas. Just to get a basic understanding of parabolas again, remember the definition, it's your set of all points x, y. And that, remember, tells us that x, y means that it is just on your coordinate plane, it's two-dimensional. So these points are equidistant from a fixed line called your directrix, and from a fixed point, your focus, which obviously it's not on the line. Well, if they have to be equidistant, they can't be on the line. So what we end up getting if we have our parabola and it goes through the origin, we know that this point here, if above, that would end up being our focus, and then your parabola everywhere has to be equidistant between your fixed point and your fixed line. So my drawing, maybe I should have had a little bit wider parabola. But I know like these two distances would have to be congruent to each other. They'd have to be equal. So there's my vertex right at the bottom there of the parabola. So your vertex, it's the midpoint between your focus and your directrix. So here's your focus, here's your directrix. It is right in the middle. Your vertex will always be on your parabola. Your axis is the line passing through your focus and your vertex. So if I go through the focus and the vertex, I'll make it red here. If I go through it, well, that's obviously becoming a vertical line. So if you connect your focus to your vertex, go down to your directrix, that will tell us that we have a vertical axis for this parabola. For our standard equation, if we have a vertical axis, it's x minus h quantity squared equals 4p times y minus k. If this, the vertex, because the vertex kind of, to me, takes the place as the center. Here, like, the circles obviously have a center to them, so you can find it. Even the ellipse obviously is going to have a center. But for the parabola, I consider the vertex to kind of be the centering point of the parabola. So it's right here because I'm equidistant to your focus, I'm equidistant to the directrix. That makes it really nice. So if your vertex happens to be at the origin, well, then we know that we have x squared equals 4py, because your h and k would be equivalent to 0. And usually whenever I have a vertical axis, or whenever I see x squared, we know that x squared opens up. We've dealt with that so many times. It's one of the first graphs that you ever learned. If you have a horizontal axis, well, usually how I look at that first is I know it's y squared equals 4px. Well, in this situation, as soon as I see y squared, to me, that means that I know I'm going to open either to the right or to the left. But that's y squared indicates that. So instead of memorizing what is horizontal axis, what is vertical axis, I just go based off of information that I've known before and not try to have to learn something new. So if I see x squared, I know my parabola has to either open up or down. If I see that it's y squared, I know that my parabola has to open either to the right or to the left. So in this situation, if we have a vertical axis, which means we have x squared, I'm going to just draw the picture at the origin, which isn't always going to happen. But obviously your vertex will be here if it is at the origin. And it can open up or down. We'll make it open up. And then we know that our focus point would be up here, so there's our focus. And then our directrix is a line. So whenever you're dealing with directrix, it has to be, it's not a very straight line there. Your directrix has to be the equation of a line. So here it's a horizontal line. So a horizontal line would always be y equals. One big thing to calculate when you have a parabola is to figure out what is this p-value. The p-value is always the number if you go from your vertex to your focus, but it has to be in that direction. It can't be focus to vertex. It has to be vertex to focus. So if you're going up, that p-value would be positive. But if you go down, let's say my parabola is opening down, from my vertex to my focus would be a negative number. So over here on the side, let's write that p is equal to the number, which you could maybe call it distance as well, but it's the number from vertex, and it has to be that order, to focus. So this is our p-value. Well, then here, because they're equal distance, if I go down, it has to be negative p. That can tell me that the equation of my directrix right now is y equals negative p. And then I can write on here that this is my directrix. And if we go back to our definition said it's a set of all points that are equidistant from a fixed line and a fixed point. So really, in my drawing, I never make my parabolas quite wide enough. But these two things have to be equivalent in length. I can make another one and say, all right, well, what if I go from here to here? Same thing. Those two have to be equivalent in length. And that's what creates a parabola. Horizontal axis, same idea. I'm going to again make my vertex at the origin just because it's easier. So there's my vertex, and if I see y squared, I either have to open to the right or to the left. Let's open up to the right. There's your vertex point. Oftentimes I just label that with a V. Focus, put it here. I label the focus with an F. And then this distance, remember, from your vertex to your focus, it has to be in that direction, vertex to focus. That is that p-value, which goes into our equation, so it always has to be calculated. I have to go equal amount of spacing back, and that would create my directrix. We can label that directrix. Oops. And now, because it's a vertical line, and directrix always has to be the equation of a line, but a vertical line we know is x equals, and in this situation, with our vertex here at the origin, it would be equal to a negative p. So that is our basic stuff about a parabola. Most of this you should probably know, but it's good to review all of it. And again, not a lot of calculus involved in this. The next page, which is kind of hard to run everything together here, I'll try to keep my graphs up on the screen so you can see it. It just defines what everything is. So our focus lies on the axis P units, and it has to be your directed distance. It has to be positive or negative. So that P value can, if you're going from vertex up to focus or vertex to the right, that's going to make it positive. If from your vertex to your focus you go down, it's negative, or if you go to the left, it's negative. You have a focal chord, and that is a line segment that passes through the focus of the parabola and has endpoints on the parabola. We will deal with this focal chord. There will be some questions that deal with that specifically. So if we draw a picture for focal chord, there should be enough room up here. And we can draw a parabola that has a vertex at the origin. So here's my parabola, here is my focus. And the focal chord, we have a line segment that passes through the through the focus of the parabola and has your endpoints on your parabola. Whoa, it passes through the focus, sorry. But in this situation, I don't want you to draw a straight line that's parallel to the x-axis, because that is a specific type of a focal chord. So try to put a little angle to it. I totally missed on that one. And good enough. If you miss it, make your focus point a little bit bigger. But you have endpoints now that have to be on your parabola. So focal chord. Now when you have a latus rectum, quite an interesting name for this, it is a very specific focal chord, and the focal chord has to be perpendicular to the axis of the parabola. So in this situation, if we draw a picture for it, again, have your parabola vertex at the origin, and we'll just have our basic x squared. That's kind of a nice one. Here, now put in there's my focus. And if we look at the latus rectum, we have to have has to be perpendicular to the axis. Well, in this situation, our axis is vertical, so we would have to have a horizontal line in there. And there are quite a few problems that deal with this, these calculus problems that deal with the latus rectum. So maybe star that, great vocab word to use. But we know here that this is perpendicular. And because it is perpendicular, these two sides then are congruent to each other. A couple other things that they're used a little bit with some of the word problems is the surface is reflective. If the tangent line at any point on the surface makes equal angles with an incoming ray and the resulting outgoing ray. We won't deal with too many things, but that's too many questions that deal with this, but it is a property of parabolas. The angle of incidence is your incoming ray, which would be like a mirror. Then your angle of reflection is your outgoing ray, like the headlights. Reflective property of a parabola. Let P be a point on a parabola. The tangent line to the parabola at the point P makes equal angles with the line passing through P and the focus, and the line passing through P parallel to the axis of the parabola. Again, really these things, you're not going to need, I don't think you need to have any of these things for your homework. So a couple of parabola examples though. The first one here is to number 14 out of your book, and this just goes back to our basic knowledge of parabolas. We want to find the vertex, the focus, and the directrix of a parabola and sketch its graph. We are given the standard equations. We have y squared plus 6y plus 8x plus 25 equals 0. Well, what I usually do is figure out what one is squared, because if it's a parabola, you're only going to have x squared or y squared. So obviously in this situation, we have y squared, and I always have to keep whatever is squared on the left side. So if it were x squared, the x's would be on the left, but because it's y squared, I have to have my y's on the left side. So I have y squared plus 6y. Well, everything else I'm going to throw over onto the right side, which means I will have to have a negative 8x and a negative 25. Again, you have to be really careful because you can't complete this square unless your leading coefficient is 1. So this one is kind of nice because it's pretty easy. You do have a leading coefficient of 1. But if you had to factor it out, make sure that you divide every term over here eventually when that would happen. Completing this square, half of 6 is 3. 3 squared is 9. If I add 9 to the left, I have to add 9 to the right. Plus, it makes this number much, much better to deal with. Otherwise, if you're dealing with negative 8 and negative 25, they don't really mesh too well. Completing the square, which is, I would always recommend doing that first. So you have y plus 3, that quantity is squared. So now basically the left side is set, which is good because that's more specific with what has to happen. This is going to equal negative 8x, and now it's a minus 16. Well, conveniently, that works out a whole heck of a lot better. If you go back to the standard equation and look, just scroll up a little bit and I'll write it down again. Our standard equation in this situation, because we have a y, would be y plus k quantity squared has to equal 4p, and then x, really this could be plus or minus, it doesn't really matter, plus or minus h. So what I always say is you have to factor out the coefficient in front of the x. So here, the coefficient in front of the x is a negative 8. That has to be factored out. Okay, well, on the left side, we just keep writing it a whole bunch. And now if I factor out the negative 8, that leaves me with x. But to get to a negative 16, we have to now make that adding 2. So that x can only be x plus 2 because of the standard equation. You can't have the negative 8 with multiplied by the x inside your parentheses. Now the last thing is to factor out a 4. So if I factor out a 4 from this, which is really easy to do, now that gives me 4 times negative 2 is obviously negative 8, and now I have x plus 2. And I like doing this because that p-value is pretty darn important. So now going through, I have to find my vertex. Remember, like I said, vertex is kind of like this center. It's a pretty important point to graph because everything, your focus and your directrix, is kind of dictated by where that vertex is. So when we list these, we have our vertex. Be very careful that you look for your x value first. So if I look at my x value, and usually we read left to right, but here to start with my x value, that is at negative 2. My y value then would have to be at negative 3. So there's our vertex. Again, always identify or find that first. Now, to get to the focus, here's my cheap way of doing things, is I know I have to move negative 2. But do I move the x or the y by negative 2? Well, the easy thing that I like to do is say, oops, I'm going to change that to red, is to say that this p-value is closest to the x variable. Therefore, it's the x that's going to change. So I know Mr. Schouts teaches different ways, and the equation looks slightly different, but this is my really cheap, easy way of doing things. So when I have to find my focus, the focus, I know that p-value is negative 2, so it has to change by negative 2, but it's the x that changes because that's what variable it's closest to. So if my focus has to change by negative 2, and I'm at negative 2, that makes it negative 4. The y does not change at all. So our focus then is negative 4, 3. Last thing to find is our directrix. And our directrix, remember, is the equation of a line. Well, I do the exact same thing as I keep this in mind, and I know that my p-value is negative 2. The equation of my line is either going to be vertical or it's going to be horizontal. Well, it's whatever variable is closest again. So here it's x, which means it's going to be a vertical line. But remember, your directrix changes in the opposite direction. So it's going to change from your vertex, and that's why that vertex is really, really important to find, because your focus goes in one direction from your vertex, your directrix will go in the opposite direction. So directrix, it's x, but I have to change my x value by a positive 2. If I change my x value by a positive 2 from my vertex, because that's that centering point, that would make it 0. On the test, I'm going to make you graph this. Partway, I do think that it makes you determine, or at least think about, does this make sense? Because everything better be evenly spaced. So if we set up our graph, and they don't have to be great, but just to sketch it, my vertex is at -2, -3. Okay, so there's my vertex. I just put a V by it. My focus is -4, -3. So there's my focus. Now that spacing is 2. And my directrix is at x equals 0. Perfect. X equals 0. I can graph that. That's a vertical line, obviously right on the y-axis. The other thing is, when you graph, you always go around your focus point. So it would look something like this, and I know that this is just a pure sketch. I don't have any other points on the parabola except for the vertex, and that's okay. I won't require any more than that. But looking at this, we know that our graph started off as y squared. Okay, well, y squared either has to open to the left or to the right. Well, obviously this is opening to the left, so that seems accurate. And then you have the p-value of a -2, which means that because it's negative, it better open to the left. So that's kind of actually a review from Algebra 2. Moving on to the next one, if you want to find an equation of a parabola and 2 points are given, your vertex and your focus, you could have your vertex and your focus given, you could have the vertex and the directrix given, the focus and the directrix. You just have to be given 2 of the 3 things. Whenever you're given points or a point in the equation, I would recommend just making a quick sketch of this. They don't have to be great. So if we quickly sketch this, our vertex is at -1, +2. So -1, +2, there is our vertex. Our parabola has to go through that point. Our focus is at -1, 0. And remember, we always go around our focus. So I start with that situation. Well, I know that my parabola is opening down. Because it's opening down, that will tell me whether I should use x squared or y squared. Well, opening down means we should use x squared. So you can start, and sometimes I just write down my basic equation. X squared equals 4py. And now I have to adjust for the center of it, which, remember, our center is like it's our vertex point. So that means it's going to be x. And I have my vertex is at -1, so I better make that a +1. That's squared. That equals 4 times our p-value. Well, I went down 2. Vertex to focus, go down 2. That's a -2. And then my y value would be y -2 to account for that 2 here from the vertex. So there is the equation of the parabola, and you don't have to rewrite it from here. You don't. If you make this -8, that's fine, but you definitely don't have to. So that's why I think a sketch is so easy for this type of a situation. All right, a couple tougher parabola problems. The first example of the, I guess, of the tougher of the two, we want to find the length of the lattice rectum of a parabola given by x squared equals 4py. Well, looking at this, I don't necessarily like it because I don't know the exact parabola that I'm given. I know that, okay, x squared equals 4py. I wish there was an exact number in there in place of p. But we know that because it's x squared, it's either going to open up or down. Well, out of convenience and what's easiest, I would always make this open up instead. That is not a very good parabola. Oh, well, you get the idea. Also, because our parabola it doesn't have a specific equation, the length of your lattice rectum will also be changing. So here, because your parabola is x squared equals 4py, that parabola can be changing depending on what the p-value is. The lattice rectum is probably will have a variable in it as well. So remember the lattice rectum, it has to go through your focus point. So we'll throw the focus point up here, and it has to be perpendicular to your axis, and this is a vertical axis. So that has to be a perpendicular line in there. Well, what I did for this, I said, well, here's a point, and I know that this point, if you think about your parabola, this has to be x, obviously, as we move over, but then how far do you go up to get to this point? And instead of calling it xy, because this lattice rectum has to be perpendicular to your axis, you know that that value is going to be p. So you have the point xp that has to be on your parabola. Well, it's symmetric, so that we know we also have the point negative xp. That has to be on your parabola. From here, I said, well, I know the equation is x squared equals 4py. And I wanted to figure out, if I plug in this point, so I'm going to plug in the point xp. If I plug in x in place of x, that doesn't change anything. That keeps it x squared. I still have the 4, I still have the p, but now if I plug this point into my equation, if I plug in my y value is equivalent to p. Which from here gives me x squared equals 4p squared. Well, remember, I'm looking for this length. So basically, I want to know how, like, I have one x value. Basically, if I make the lattice rectum, I would have the length of 2 x's when it comes down to it. So I want to solve for x. Well, that's easy to do from here. We can take the square root. And x would equal plus or minus, but whenever I'm finding a length, I want this to be positive. And I'm multiplying, so properties of radicals, I can just take it as it's 2p. Well, if my x value is equal to 2p, and I want the length of the lattice rectum, I have a 2p here, and I have a 2p on that side as well. Therefore, the entire length is going to equal 4p. All right, one more. Number 82, we have a simply supported beam. I'm pretty sure that was supposed to be beam. You might want to make that an M. If it's a beam, it'd be awfully hard to stand on. And it's 16 meters long. So right now, to start, our beam is 16 meters long. It has a load, so this guy is considered to be a load, and it's concentrated at the very center. And then obviously see your figure, so here's our figure. The deflection of the beam, maybe I was hungry that day, I'm not really sure, at its center is 3 centimeters. So we're moving down 3 centimeters. So, you know, if it were just a beam, if it were a beam, it should be a straight line. But our load, our heavy guy, is pushing it down 3 centimeters. One bad thing, we don't like combining meters and centimeters here, but we'll deal with that. And assume that the shape of the deflected beam, oh good, I'm back on track, it's a beam now, is parabolic. So we have a parabola here. First of all, find the equation of the parabola, and assume that the origin is at the center of the beam. And usually you're going to do that. So what I would do is draw in my coordinate plane. Make it nice and thick here. So if I draw in my coordinate plane, and they said we want to assume that the origin is at the center. So here would be the center. That should be our origin. And it does, like it slowly is gradually going up. But remember, our beam is 16 meters and we only have a deflection of 3 centimeters. That's a pretty strong beam. Maybe there's more, well, it only shows support on the ends. Kind of unrealistic, I think. All right, so to write the equation of our parabola, if we look at it, again, we know that this is going to be in terms of x squared. So for letter A, we know we're something in the form of x squared equals 4py. Well, we also drew this so that the center is at the origin, so that's really nice because our vertex then is 0, 0. So if our vertex is 0, 0, great, we can just keep that there. And now we have x squared equals 4. We need to calculate our p-value times y. Well, to calculate the p-value, here would be, let me make that red for us. This point up here would be your focus point. So then, if this is in terms of meters, we should probably have this in terms of, or either make them both meters or both centimeters. That's really up to you. Okay, I think I actually made a mistake here. I don't think that we should be able to assume that this is your focus. I actually would say that that's a really bad idea. So we're going to erase this part of it. I hope you're using pencil. And there's something that we can say, that we can do that is much more accurate. And we can say that we know that here is a point on our parabola. So this point on our parabola would be 8 meters if we go from our center. So here would be 8. And if this is 3 centimeters, we have to convert everything to meters or centimeters. I'm going to use meters. 3 centimeters in terms of meters. Does anybody know what that is? And that is 0.03 meters. So this point, actually, I'm going to write it over here. The deflection here, that would be 0.03 meters. So I know that it's x squared equals 4py. Well, I also know that this point of 8 meters and 0.03 meters, I know that that's on my parabola. Well, if I plug this point into my equation, I can solve for p, and you'll actually see that p is definitely not 3. So if I plug in my point, I have 64. I plug in 8 and square it, equals 4 times p times the 0.03. Well, that gives us 64 equals 4 times 0.03 will give us 0.12. P divide by 0.12. P is going to equal, I believe it was 1600 divided by 3. So now when I write my equation, it is x squared equals, I took 4 times p when I wrote my equation. And you could leave them separate if you wanted to. But I did 4 times this p-value. And that gave me 6,400 divided by 3. And then I still have the y. So here is the equation. And you can see that p, that distance, is definitely not 3 centimeters. And now here's the equation of my parabola. For b, how far from the center of the beam is the deflection 1 centimeter? So this is a little bit deceiving or a little bit tricky, because if your deflection is 1 centimeter, that would be way over here. So way over on either side. But it would only be 1 centimeter going down. So right here, you know, it's 3 centimeters. Whatever here, it would be 2. I want that deflection to be only 1 centimeter. Well, remember now we have to convert to meters, so 1 centimeter in terms of meters would give us 0.01 meters. So what I did for B, or how I thought about this, is I want to know how far from the center. So if here is my center and I want to know how far is this, well, that's the variable that I'm looking for. That's that x value. And that's what I want to find, how far from the center. And my deflection is only the 1 centimeter, or the 0.01 meters. Therefore, my y value, I would actually have to go up 0.02. I hope that makes sense. So here, if the deflection is 1 centimeter, I'd have to go up 2 centimeters. now I'm going to plug this point into the equation. So if I take this, plug it in, well, x stays x, and now I have to square it. And then I'd have 6,400 divided by 3, and my y value is 0.02. When I solve this, x squared equals, I don't have what this number was, 6,400 divided by 3, and then times 0.02, I got 42.66 repeating. Well, I know that I want the square root of it, so I guess we could write that in here, 42.6 repeating. And I want just x, so the square root of that value. X is approximately 6.532, usually round to 3 decimals, meters. And that makes sense. If it entire thing is 8, well, 6.5 seems pretty realistic. And that really could go in either direction, to the right or to the left. So that's circles and parabolas. Kind of a lot of information, and that's why we divide this up into 2 days. And the assignment, I'd have to get it, I gotta pause just a second. All right, so it was at the end of this. Circles and parabolas for your homework, page 704. Pretty short to start today. So I would recommend getting this done, because obviously you can see tomorrow there's a lot more questions, and they're a little bit more complex when it comes to the ellipse and hyperbola. So circles and parabolas, page 704, numbers 13, 15, 17, 23, 25, 81, 86, 88, and 91. Good luck.